In this lesson, we are going to be talking about intervals of increase and decrease. Now, I know there's no notes page. That's because for this one, I just figured it was better to show you. So if you have a blank sheet of paper, I would get that out, and all you're going to do is follow along. Okay, so intervals of increase and decrease. You've actually already learned about this before when you studied polynomials in pre-calc. And remember, when we talk about intervals of increase and decrease, we are talking about where a function is going up and where it is going down. So I've sketched just a quick example of a function for you, and I could say we are increasing along this interval here up until the very top point. And I could say we are also increasing along this interval here from the bottom of this point to the rest of the function. And then if I'm talking about decrease, of course, I could say we're decreasing between these 2 points. All right, so the yellow represents me going up the function. The green represents me going down. So yellow is increase, green is decrease. All right, and I'm going to write that out for you off to the right. Okay, so for increasing intervals, we say those are intervals where f of x is going up, and for decreasing intervals, we say those are where f of x is going down. Now that's how you learned it before. In calculus, we're going to take this idea and extend it by saying if a function is going up, if I were to take the slope at any point along the increasing interval, I would get a positive slope. And if I were to take a slope at any point along the decreasing interval, I would get a negative slope because it's going down. So calculus takes this idea one step further and it says, all right, the actual definition of increasing is where the derivative of x is greater than 0 or positive, and then decreasing would be where the derivative of x is less than 0 or negative. All right, so let's say you're not given a picture of a function, you're just given a function, and you were told to sketch what that function looks like. You can actually kind of figure it out, having never seen it before, using this concept. So that's what I'm going to show you next. All right, so in the next section of our blank page, we're going to try just this quick problem. It says given f of x is equal to x to the fifth plus 5/4 x to the fourth minus 20x cubed minus 7, find all extrema and intervals of increase decrease. So once again, I am not given the picture here, and I'm going to try and use the derivative of this function to figure out where my extrema are. So remember, those are hills and valleys, and where I am increasing and decreasing. So in one of the previous videos, you learned that, first of all, if this function is continuous, that means there must be at least one maximum, so one hill, and one minimum, so one valley. So first of all, I know that f of x is a polynomial, and I know that all polynomials are continuous. So I can conclude that f of x is continuous. Which means I can use the extreme value theorem to take the derivative and find the critical points. So I'm going to use EVT, and I'm going to say f prime of x, so I'm going to go ahead and take the derivative, is equal to 5x to the fourth plus 5x cubed minus 60x squared, and then of course that 7, if you derive it, it turns into 0. So this is what we have. And I can use this function to determine where the critical points are. So remember, those are potential points for maximum values and minimum values. All right. So to find critical points, remember you have to set the denominator equal to 0 or figure out where it's undefined. So first of all, this is also a polynomial. So this is continuous everywhere, so it's never undefined. So now I just have to figure out where this function is equal to 0. Once I have those points, I'll know where my potential hills and valleys are. All right, so we can factor this a bit and use this to figure out where those points are. All right, so the first step in factoring is realizing that all of these terms have an x squared in common. So I went ahead and pulled that x squared out, and I divided it out of each term, and whatever's left is in the parentheses. Okay, I can keep doing that, looking for common terms. So the next step I did was I recognized that, all right, now each of these terms have a 5 in common. So I went ahead and pulled that 5 out, divided it out from everything, and x squared plus x minus 12 is what I have left. And then finally, this is just a quadratic that I know how to factor into its two separate parts. So x squared plus x minus 12, that's the same as x minus 3 times x plus 4. Okay, so now I've completely factored the derivative into 1, 2, 3 factors. Now I got to figure out, by setting each of these equal to 0 and solving, I can figure out all the values of x that are going to give me 0. In other words, I'm going to figure out all the values of x that are going to lead to that critical point. All right, so I've done that off to the right here. Setting 5x squared equal to 0, I get x equals 0. Setting x minus 3 equals to 0, I get x equals 3. And setting x plus 4 equal to 0, I get x equals negative 4. And these are my critical points. So remember, these are just potential locations for minimum and maximum values. Okay, once I have done this, I can use what's called the first derivative test to figure out exactly where all the extrema are and where I am increasing and decreasing. Now, the next lesson is also called first derivative test. There's going to be another video where there's more practice, but I'm just going to show you how it works right now. So the first thing I'm going to do is make a table. And that table is going to look something like this, all right? We've got a place to put our intervals. We've got a place for test values, f prime of x, and a conclusion. And I'm going to show you how to use that. All right, so I have 3 critical points up here. All right, I have x equals 0, x equals 3, and x equals negative 4. So if I think about that, if I think about each of those points as a natural break in the function, then I can set up a bunch of intervals along this table. So if my first critical point occurs at x equals negative 4, well, that means the graph was doing something from negative infinity all the way to 4. And then remember, this is where the derivative is equal to 0. So at negative 4, sorry, excuse me, this should be negative 4. So at negative 4, my slope is now flat. And then it picks up at negative 4, and the graph continues on to the next point, which would be 0. So it does something in between that interval. And then finally, picking up from 0, it goes all the way to 3. And then picking up from 3, the graph does something all the way to infinity. All right. So as you can see, I've used my critical points to create some natural breaks in the function. So every time I hit a critical point, I broke it up into another interval. Okay, and now what we're going to do is we're going to take the derivative at different values in between each of these intervals to figure out if the derivative is positive or negative. Because if it's positive, remember that means my function was increasing, If it's negative, that means my function was decreasing. All right. So I just have to look at this first interval and pick a value in that interval. So I'm going to pick -5 because -5 is in between -infinity and -4. So I'm going to say x equals -5. Then I'm going to do the same thing for this interval. I'll say x equals -1. And then in this interval, I'll say x equals +1. And then finally, in this interval, I could pick 4. All right, and what I'm going to do is I'm going to plug each of those values into the derivative function to figure out whether or not I get a positive or a negative. So I'll show you one of these, all right? I'll show you -5, for example, and then we'll just use a calculator for the rest. So remember, if I'm going to plug in -5, I need to know what f prime of -5 is. And I'm going to go back to my main derivative function here. And every time I see an x, I'm going to replace it with a 5. So I have 5 times 5 to the 4th plus 5 times 5 cubed, and then minus 60 times 5 squared. And plugging this into a calculator, I get that this is equal to 2,250. So I could say f of -5, sorry, f prime of -5 is equal to 2,250. And I'm going to do the same thing for x equals -1. I'm going to plug -1 in, and then x equals 1, and then x equals 4. All right, and when I do that, I'm going to get f prime of -1 is -60, f prime of 1 is -50, and f prime of 4 is 640. Okay, now, once again, we're going to use that conclusion from the very beginning and say, okay, if my derivative is positive, okay, that means between this interval, this function must be increasing. And if my derivative is negative for the next interval, that means along that interval, I must have been decreasing. So I'll put DEC for short. Same thing here. In this interval, I got a negative derivative, so that means must have been decreasing. And then finally, in this last interval, my function must be increasing. Okay, now, this table is called the first derivative test. It is just a quick way to figure out some information about a function, even if you weren't given the picture. And from this table, I can actually sketch what this function should kind of look like. Okay, so here I've sketched a quick set of axes, and I've gone ahead and marked the 3 spots where my critical points are going to be. In other words, where my graph should flatten out because the derivative was 0. Okay, now all I have to do is look at these conclusions and figure out what's going on. So if at my first critical point here, if I've gone from increasing to decreasing, in other words, from going up to going down, that means my first critical point should have been the top of a hill, all right? And I can figure out where exactly that point is if I plug -4 back into the original function up here, right? So if I do that super fast in a calculator, I will get that f of -4 should be about 569. So my point where my hill happens is going to be at -4 comma way up here, 569, right? Okay, So there is my first, and it looks like I went from increasing to decreasing. Now, on the next critical point, I went from decreasing to decreasing. So I was going down, and then I flattened out, and then I went down again. So this is not really a hill or a valley. So this is not an extreme point. And that's okay. Remember, critical points just tell us where extreme values might be. It does not guarantee that they're there. So I went from the top of this hill down to 0, and then I went down some more, all right? And then at this last point, okay, at x equals 3, I went from decreasing to increasing. So this must be the bottom of a valley, a minimum value. Okay, and one last thing, I can figure out where f of 0 is on my graph by plugging 0 into the original function. I'm going to get -7. And then I can figure out where f of 3 is, my last critical point, by plugging 3 into the function. And that is -405.25. All right, so going back down, I know at 0, I'm slightly negative, and at 3, I'm very negative. Okay, now follow your conclusion. So from negative infinity all the way to that first critical point, we were going up. We were increasing. So something like this. And then we started decreasing towards 0. And we kind of flattened out at 0. So I'm going to flatten it out just a little bit. And then I'm going to keep decreasing down to this last point. And then I'm going to increase after that. So now I know if I were to graph that original function, x to the 5th plus 5/4 x to the 4th minus 20x cubed minus 7, I should get something like this, all right? And I can say, finally, that these are my increasing intervals. This one big interval I can actually combine into one from -4 all the way to 3 because I was decreasing that whole time. So this is my decreasing interval. And I can say, lastly, that I have a, looks like an absolute maximum value at x equals -4. And I have an absolute minimum value at x equals 3. Okay, so that is how you use the first derivative test to figure out how a function behaves without its picture.